Okay, welcome back to the computational thinking course. This week we saw a slightly different kind of thing in the course, which is we saw how how we can organize the programs or the code that we are writing in a way that allows us to do multiple things at the same time. Okay, so far we have never seen that. So this is the first time we are trying to see whether we can do things together, right, simultaneously, and what kind of problems that can lead to and so on. So specifically, so we are interested in understanding this idea of this notion which is called concurrency, which lets you deal with handling things, multiple things at the same time. So specifically the procedures we have seen so far, only one step. So procedure contains a sequence of steps. Steps can be iterated, can be repeated, you can do loops, and you can do if then else's and so on, but at any given point in time if you ask where are you in the code, you can point exactly to one line in the code and say this is where I am. Okay, so at any given point in time you are at one step and that's the only step that will be executed. Once that step is executed, it might move to another step based on how the code is structured, but any given point in time only one step is executed at a time, right? But in real life that is not how it works, right? Because we have seen basically that when multiple people are doing things, I am here, I am doing something, you are sitting, you are doing your thing, meanwhile somebody else is doing something else and so on. So different people are doing things concurrently or simultaneously, right? So in real life many things are going on at the same time, which means that multiple steps could be happening simultaneously, and when you have multiple steps happening simultaneously, this thing is called concurrency, right? Now we want to have a simple way of representing concurrency, right, putting it down in some kind of codified form, and to manage it in a way that it does not create problems for us. Okay, so what kind of issues can come up because of concurrency and how do you manage those issues is what we are going to discuss, or what we have been discussing in this week, right? The lectures that you have already seen this week, and this one we will actually expand on that a little bit more to understand the concepts by fixing them in some kind of codified form, alright, on which you can basically then work on problems and so on based on this. Okay, so specifically we can consider that there are two procedure calls P and Q which can be called concurrently, right? We can call a procedure P and then we can call another procedure Q, and P and Q are executing together. So P is at some step, Q is at another step, and then P proceeds to one step, Q proceeds to another step, they are going on together. So how do you do this? How do you call procedures P and Q concurrently? Now to start with, this is not possible currently in the way we have written things, because when the caller calls the procedure P, it will call P is basically, and it passes some parameter to it, P executes, it finishes and comes back. Meanwhile the caller is waiting, right? The fellow who called P is just waiting, and when P finishes its computation it returns a value back to the caller, and then only the caller continues. So somehow we must allow the caller to start P or call P and then not wait, do something else. Okay, so it means that we have to unbundle, right, this procedure call. Procedure call is doing too many things right now, so we have to unbundle it and break it into its components. What are the things? Let us consider. So we know this is a beautiful thing that procedures do for us, right? It allows you to write things like this, right? B equal to P of A. So B equal to P of A basically means that we are basically calling procedure P with the argument A, and then basically the procedure P executes, and then it finds the result, and then it returns the result, and then this result is stored in P. All of that, right? All these things, business of calling procedure P, passing it parameter A, then P doing its work, then it computes its result, and then it sends the result back, and then the result is put in B. It's all written in one line, B equal to P of A. Very neat, cute way of writing things. Okay, but the problem with this B equal to P of A is it is bundling too many things in it, so we can't do concurrency. So let us unbundle it, right? What are the three things that we are doing here? We are first starting the procedure P and passing the parameter P. So that is the first step, right? We are starting procedure P, passing the parameter A to it. Then what are we doing? Then we are saying caller is waiting for the procedure to complete its work. This is another thing. While procedure P is working, that means it has taken the parameter A and it is doing its work, the caller is waiting. So the caller is waiting with what? The caller is waiting for what? Partner is waiting for the procedure to complete its work. So we have to know whether the procedure has completed its work. Procedure has to be able to tell that it will complete its work, right? So that is the other thing. Third is the procedure, when it finishes completing its work, it has a result. It must send the result back to the caller, and then the result must be stored in B by the caller. So there are three different things going on, and unfortunately when we wrote B equal to P of A, it is a cute, nice way of writing, compact way of writing things, but that compact way of writing things is good for sequential programming. In concurrent programming it basically comes in the way, so we want to unbundle. Okay, so we want to break it down into three different, in some sense, calls. One which will start the procedure P and pass parameter to A, another which will wait, and the third which will accept the result. Three different calls we want to make. Now usually concurrency, it's nicer to visualize concurrency in the context of object oriented programming. Luckily we have discussed last week object oriented programming. So in the context of object oriented programming, it's very easy to understand, because just like I told you, I am doing something, you are doing something, and so on. I and you, we are all objects in some sense. So if I have two objects X and Y, X can be executing its procedure PA, while Y is also executing its own procedure PA. So class teacher can be computing the average, while physics teacher is computing average, math teacher is computing average, and chemistry teacher is computing average. All four are computing average here. So four can be working concurrently, right? So for objects X and Y, they can call their own procedures concurrently, right? They can call the procedures may be running concurrently. So it's nicer to think about concurrency together with objects. And in fact, in this lecture, we are only going to talk about concurrency in the context of object-oriented programming. There is concurrency in the general context of normal procedural programming, but we are not going to discuss it, right? We are discussing it in the context of object-oriented computing. So we said we want to unbundle a procedure call into three parts, right? So the step B equal to X dot PA. Instead of writing PA, I have said X dot PA. Remember, PA is a procedure which is a public procedure of object X, so I can call it, right? And then I can find it, and it returns the result, and I can store the result in B. B equal to X dot PA, which is a cute, nice way of, compact way of representing things. We want to unbundle that, right, into three parts. The first part is start the procedure X dot P and pass the parameter to A to it. I must have a way of writing it. So let us say I write it as X dot start, which means that object X implements a generic procedure called start, to which you give a procedure name and a parameter, and it will start the procedure with that parameter. Okay. Then I want to wait for the procedure X dot P to complete its work. So the X dot P has to be able to tell me it has completed its work. So how does it do that? Let us say object X, need not be P that tells, right? Object X, if it tells that. So let's say object X has within it a flag, right, which it sets when P is finished. When P is finished, it will set that flag. And object X basically can have a procedure called ready, which you can call, anybody can call ready. And what ready will do basically is will check whether the flag corresponding to P has been set. So you give it P as a procedure, and it will check whether P is flag, that means P completion flag, whether it has been set or not. If it has been set, then X dot ready P will return true. If it has not been set, then X dot ready P will be returning false. Obviously, when you start X dot P, the first thing that when you start X dot P, that means when you call X dot start PA, the first thing that start thing has to do basically is to set this completion flag to false. So that basically if somebody asks, are you ready, it should say false, right? So you can check whether or not the object is ready by calling X dot ready. But when do you check? So maybe the caller can keep checking. So object X can poll. It's called polling. Polling means you can repeatedly keep calling and checking, right? Keep checking. So it can check repeatedly, put it in a while loop and check whether or not the P is ready. So whether X dot ready P is true or not, you can keep on checking by using polling, right? You put it in a while loop, and you need to wait, right? I can put it in a while loop, but what is the while loop doing other than checking? It has to wait for some time. So a much better way is to write a nice function called wait. And what wait will do basically is, and wait for a condition, wait C, right? And what wait does is it puts the caller in a wait state and will wake up the caller once C becomes true. Now, of course, how this is implemented is a very interesting concept in operating systems. When you get into operating systems much later on in your final year, you might want to think about how this is implemented. Things like this are implemented. But usually systems have a way of waking up things from sleep and so on, and we are going to use one of those methods. So let us say that the caller is put to sleep and will be woken up when the condition C becomes true. Okay, so wait C basically makes the caller to wait till the condition C becomes true. So we can put these three things together. These three things: object X has implemented a procedure called ready. For each procedure, which will tell you whether or not that procedure is finished or not. Then the caller basically will keep checking whether ready P is true, and it does that by actually using this wait condition. Wait for. What should we wait for? What is C in this case? What should we be waiting for? Obviously, should wait for x dot ready P. So the simplest thing for the caller to do basically is to wait simply for x dot ready P. So and when does x dot ready P become true? X dot ready P becomes true when procedure P finishes, and then procedure P sets the flag to true, and that basically makes that x dot ready P call come out as true. So wait x dot ready P will basically become true at that point in time. So so we saw two things. One is how to start a procedure. You start a procedure by calling x dot start, give it a procedure and a parameter or bunch of parameters. The second is to check whether or not the procedure has completed its work. You do that by waiting for x dot ready P. And now we need the third thing, which is basically assuming that the procedure is ready, which means it has completed its work, I must pick up the result. Okay, so you have to have a way of picking up the result. So we can write a third function that x implements, which is called result. So remember, we have written already two functions that x implements. One is called start, another is called ready. Now this is the third function, result. So x implements a function called result. You can call x dot result and pass it the procedure name as a parameter, and it will return back the result of it. So the code for concurrency therefore consists of unbundling the procedure call into these three phases. Let us look at it with an example. I mean, it's always easier to understand with an example. So let's go back to our classroom data set. So we saw basically that class average is a data type that we defined, which found the average of different things. So class teacher, for example, would find the total average, math teacher would find the math average, physics teacher would find the physics average, and so on. So let us say we want to find the maths and the physics average in parallel. How do we do that? We create a math teacher object, we create a physics teacher average, and we want to call math teacher average and physics teacher average in parallel, right? We want to call them concurrent. So recall that class average had the following fields. It had marks list and a value as the fields, and here it had public procedures average and add student marks, right? Add student two public procedures. So to make average concurrent, the class average procedure has to implement start, ready, and result, right? It has to implement start, ready, and result. I didn't write start here. It should implement the procedure start average, ready average, and result average. Okay. Now for start average, we have to implement it. I mean, there is nothing we can do. So assume basically there is a procedure that basically starts the procedure. Means basically start PA will just call P of A, right? That's what it should do. So that's relatively straightforward, but we have to implement it. Now assume that what about ready average, right? Now we have already a field A value which seems to do it, because remember, how did we write the code for average? The average code for class average said basically that check whether A value is -1. If it is -1, compute the average and put the average result in A value. So if A value is not -1, it basically means that average is computed, finished computing. Okay, got its result. A value has the result. So nothing to do. So A value is already in some sense the flag for checking whether the procedure has completed its work or not. If A value is -1, it means it is not completed. If A value is positive, it means it has completed, it finished its work. So A value is already the flag that we need. Okay. So all we need basically for ready is to return A value greater than or equal to 0. The Boolean condition A value greater than or equal to 0, you can return that. So if A value is greater than or equal to 0, then ready will return true. If A value is not greater than or equal to, which means A value is -1, then ready will return false, which is all we need. Okay. What about result? Now the result of computation of average is A value. So result just needs to return A value. So trivial. Okay. So start of PA will just call PA. Done. Okay. What does ready average do? It checks A value greater than or equal to 0 and returns it. What does result average do? Just returns A value. Very simple procedure. All these three procedures are extremely simple, and by using these three procedures, we have now made, in some sense, our average procedure concurrent. Okay. So suppose we want to do maths and physics averages in parallel. This is the code for it. What we will do, we'll call maths teacher's average we want to start. Now we are not passing any parameter here because average doesn't take a parameter.
So we say MAT dot start average, which means we are starting the average for maths. Then physics teacher dot start average. So we started the average for physics. Now we are not waiting for average to compute. We started the average for maths and then proceeded to start physics average and then proceeded. Okay. Now both average maths and physics are running now. We don't know what's going on, they are running. Okay. Now what do we wait for? You have to wait for both of them to be ready. How do you do that? Remember that ready is a boolean, so we can do AND. So I do MAT dot ready math teacher dot ready average and physics teacher dot ready. I wait for both of them to become true. When both are true, at that point in time the wait condition is true, so it comes out. Okay. So when it comes out, basically at this point both of them are ready. Now I need to read the result. How do you read the result? I call math MAT dot result average. So that gives me the maths average and I store it in average maths, and I call physics teacher dot result average. I get the result for physics and store it in average. So I have, as you can see here, I have unbundled because I have unbundled the calls, right? Because I unbundled the calls, therefore I can do the start, I can do the starts and then proceed without waiting. I can start physics, I can start maths and I can proceed, and then I can wait whenever I want. I can wait for both of them to become ready, then I can read the result and store it. So this unbundling allows me to do things concurrently. Of course this code is looking much more complicated and involved than just writing average maths equal to MAT dot average bracket, done, right? Such a cute code, and average physics equal to PhD dot average, but that means basically you can't be concurrent. If you want to do concurrency, there is a cost, right? In some sense you have to, there is a cost in terms of coding that you have to do in order to structure the concurrency. So this is what you have to do. Alright. Now note that the caller is waiting for both maths and physics teacher to become ready through that boolean AND, right, which is there between the two. Alright. Now consider that we have two objects, math teacher and physics teacher, and okay, we want now to do not only average, we may want to do add student also concurrently, right? We have math teacher and physics teacher objects and they have add student procedures. Why only average? Let us also make the add student also work concurrently. How do you do that? For that again same way, we need to implement ready new student. It's not new student, it's add student, right? I'm sorry. It should say ready add student. And how do you implement ready add student? Ready add student basically can again use a value, because we know that the result when add student finishes, a value is set to -1, right? So how do we know add student has finished its job? You know add student has finished its job when a value is -1. So just look at a value and you will know whether add student. So that same a value can also act as a flag to see whether or not add student has finished. So ready add student can just return the boolean value, a value equal to -1. And what is the result? We don't need a result because add student is a procedure which has no result, right? It's just adding a student to the marks list and setting a value to -1, otherwise it doesn't return anything. So add student doesn't return anything, so we don't need to implement the result function. So very simple, right? So we have now made both average as well as add student concurrent. Now I want to take you to something that's I'm going to see how things can get a little bit complicated, right? So let us say, for example, now I want to do okay, I'm showing you how to, we didn't talk about the code. So to basically do the code concurrently, add student concurrently for physics and math, we do mat.start add student new mark 1, physics teacher dot start add student new mark 2, and then you wait for both maths and physics students to be ready, right? That's what you do. Now I want to do basically something much more interesting, right? What do I want to do? While average is executing, I want to add a new student. Okay, while average is executing, I want to add a new student. What does this do, right? So I start average and I start add student. In parallel, I want to do both of them because average is concurrent, add student is concurrent. So in principle, I can also call average and add student concurrent. So that's what I want to try. And I want to wait for both average and add student to complete, right? And then I want to take the average of average result and put it in average math. So I'm calling the same object. If it were different objects, maybe things would work out okay. But the same object maths, I want to call basically for math teacher, I want to call it average and add student at the same time. You already see that this is going to create problems, but let us see what kind of problem this creates. Alright. First problem we see is that there is a conflict in a value itself. Remember that average will set a value to 0 or a positive value at the end, add student will set a value to -1 at the end. So either a value is 0 or a positive value, or a value is -1. It can't be both. Okay. So remember that for ready average, we said just check whether a value is non -1, and for ready add student, we said check whether a value is -1. Now both of them are not possible. So it's not possible for a value to be both -1 and to be not -1. So which means that the weight, while innocent, if you look at that weight, mat.ready average and mat.ready add student, it looks very innocent. It looks as if the correct thing, right? You are saying wait for average to become ready and wait for add student to become ready. Correct thing to say. But you see the way we implemented it, it's never possible for both average as well as add student to be ready. So that wait will wait forever, right? It's never going to end. So it's actually a perpetual loop. So it's wrong code, right? We made a mistake in the code. What is the mistake? Mistake was trying to use do too much work with this a value. The same a value we are using as a flag, using it to store the result. We are doing many things with it, overusing it. So let us say, okay, I don't want to be so greedy. I have any number of fields. Why am I being stingy with fields? Let us add some more fields, right? So let us say we explicitly add two fields. One is called average ready, another is add ready. Average ready will tell you whether the procedure average has completed its work or not, and add ready will tell you whether or not the procedure add student has completed or not. Okay. So when add student finishes, it will set add ready to true. Similarly, when average finishes, it will set average to true. So that should take care of it. Now, add student has two things to do, right? One, it has to set a value to -1, and then it has to set add ready to true. Strictly speaking, it can do this in any order, right? It really doesn't seem to matter. Similarly, average also can set, we'll see, okay. The average also has to set two fields to after it finishes. One is a value and another is average ready. Both of them have to be set. So in the case of add student, right, it looks like we can set the a value and add ready in any order. You could set a value first and then set add ready, or add ready and then a value, nothing may go wrong. Okay, it looks like that. We'll have to see, right? But definitely there is a problem with average, right? Because assume for a moment that when you're writing the procedure for average, at the end of average you set a ready, average ready to true, and then after that you are going to set a value to -1. You're going to set a value to the average value. So it means non -1 value, right? So the minute you set average ready to true, it may turn out that just as you did that, the caller basically checked for the condition ready, and he found that basically average is ready. And because he found average is ready, right? How does he find out average is ready? He found out average is ready because the ready returned true. And when did ready return true? Ready returned true because average ready is set to true, right? And which you already set. So it returned true. So the caller basically found that the procedure is ready, so it immediately calls for the result, right? So it calls for the result, and it may just so happen, right? Of course, chances are very low because there are a lot of things happening from outside. This is happening inside. So between setting average ready to true and calling a value to minus, only a few microseconds may take place. So it may happen. Actually, nothing may happen, but there is an odd chance. There is a possibility that there may be some delay between setting average ready and a value to -1. In that delay, it may happen basically that ready is read by the caller. Caller thinks that average is ready and so calls for the result. And what will happen? This guy will return the result. What is the result? Result is a value. He will return -1. So possible that there is a race condition, very small chance, but there is a possibility there is a race condition in which you ask for a result and actually get a nonsense result like -1. So therefore you must set a value first and then set average. There are like this, when you do concurrency, you will find basically that you must respect the sequence in which things are done much more carefully than you would do in normal procedural programming, because from outside any order things may come to you. Okay. Now there is a slightly more interesting or more complicated problem that comes because of concurrency. In this case, what could happen basically is that you call average and you call add student, let us say, in parallel concurrent execution. We already saw basically that if you try to do it with a value, that ready average and ready add student will basically do forever. So we took care of that, right? What did we do? We kept a separate flag called average ready and add student ready, add ready, and we checked for that. And so at least now we know that weight is not looping forever, it will come out of the weight. But the question we can ask is, when we read the result of average, what is this result? What result is coming out? Is this result including the new student who has just been added, or is this result before the new student was added? We don't know, because we called both of them together, right? We called average and new student together. So did the average get computed before the new student was added, or did it get computed after the new student was added? Now, if it so turned out that the average had computed, finished processing the entire list, and after that the new student was added, then it will return the old value of average. It means the average without considering the student. Or if it turned out that add student was faster and it finished appending the student to the end of the list, and then average started computing, then it will find basically that average will include the new student. So average could either be including the new student sometimes, or sometimes maybe not including the new student. So it's ambiguous in some sense. But something worse can happen, right? What happens if average is processing the list? It has come to the last element in the list, and it is going to check whether that last element is indeed the last element. Which means it's coming to the end of the last element of the list. At this point, add student starts inserting the element into the list. So while one guy is trying to read the end of the list, another guy is trying to change the end of the list. What will happen here, we don't know. I mean, something crazy can happen, right? It's possible that the list is completely corrupted as a result of this operation. Many times system may crash and all that, okay? Erroneous list can be corrupted, and subsequent calls will all crash, and all this nonsense can happen. Therefore, you must be very careful about calling two things concurrently when they access the same thing, like a list and so on. Okay, so you want to prevent two people from accessing the list at the same time. How do you do that? You do that by making the list operations what are called atomic. You say the list field is atomic. Atomic means that only one person can enter it at one time. Two people can't access the list operation at the same time. If one list operation is running, like for example append is going on, all the other list operations are made to wait. Okay, so if you are trying to do a first with the list, then every other operation that is waiting to do things with the list like rest, append and so on, they'll all have to wait. So only one at a time, right? Single thing at a time. That is why it's called atomic, right? So if you make the list atomic, the list field atomic, which means all operations of the list are atomic, then you can prevent this kind of race conditions, and we would be safe, right? So one can argue, I mean, the point is that this looks very artificial. One can say, I mean, nobody is going to call add student and average at the same time. Why would the caller call add student and average at the same time? He knows he is going to add a student. Why doesn't he just add the student and then call average, like what I have written here? Call add student, wait for ready, then call average, wait for ready, then find the average. Even if you want to do it concurrently, do it like this. So do it sequentially in a sense, right? Don't try to do it concurrently when you know anyway you're going to do both of them. Might as well do it correctly, in the right order. The answer is, it may not be the case that the same guy is calling both these procedures. You might have one object X which is calling add student, and different caller Y might be calling average concurrently. So two people may be calling the same object, two procedures at the same time, and it's not possible for X to talk to Y and find out, are you going to call, if X is asking Y, are you going to call? If so, then I will wait. You finish your call, then I will call. How do you coordinate like that? It's very difficult for X and Y to coordinate. So because it's very hard for X and Y to coordinate, therefore, and we don't know, we can't prevent, in fact, because both of these are public procedures, we can't prevent anybody from calling and at any time. Therefore, it's necessary for us to plan for concurrency, right? We have to plan that if there are two procedures, there is possibility that both of them are called at the same time, and therefore they can both access the list and the list can get corrupted. So we have to think, when we are doing concurrency, we have to think about all these possible cases that can come up and protect all these kind of cases by making things atomic to the extent possible. Okay. Now I want to finally come to another model which is called the producer consumer model. Okay. So far what we saw basically is that the caller started the procedures and then just waited for them to finish, which is what we call polling, right? Now what if the caller does not want to wait, wants to do also something, right? So wants to do concurrently something. So it may turn out basically that the caller calls the procedure, say math teacher, and asks it to find average. The caller is also doing some work. So now the math teacher, when it finishes, it publishes ready, right? and it has got its result and so on, but this result it has to hold indefinitely because it doesn't know when this guy is going to call, right? It may, in the earlier case, in the case of polling, I know that minute I put ready, I know that that guy is just waiting for me to become ready, so as soon as I become ready, he will take my result. But now I don't know, right? I don't know when he is going to, should I just keep holding this result? Should I just prevent other people from calling me till I have passed on the result? What should I do, right? So this is quite complicated, right? This is complicated. So there are two ways to deal with it. One is the procedure can preempt the caller. It says, I don't care, you are the one who started me, so I have finished my work, whether you are doing something else or it's not my business. I will stop you and I will give you the result. If you are in a classroom teaching, I will interrupt you in the class and I will give you the result. Something like that. Okay. So this is called preemption, and in order to implement preemption, we need a number of things like interrupts and so on. We are not going to discuss this method further here. We are going to discuss another method which is a much easier method, which is called the producer consumer model. This is what happens basically, is that the caller says, look, I want to do something while I am calling you. So therefore what I will do is, I call you. Now I really don't want to know whether you have finished or not. You just, when you finish, whenever you finish, right, you put your result in a buffer. So how do I, so I pass the buffer to you, I give you a buffer, and I tell you, or a tray, whatever it is we called in the lecture, and I tell you basically that you put your result in this buffer, and I know that you have finished because I can see that the value has come in this buffer. Okay, this is the way it's done. So in the producer consumer model, the caller is the consumer and the object whose procedure is being called is the producer, because that's the guy who's doing the work for me. So the worker is the producer, or the subcontractor is the producer, and the contractor, the guy who's asking for the work to be done, is the consumer. So consumer can also queue up tasks for the producer, but we are not looking at this particular kind of case here. So to ensure that the producer knows where to write the results, I pass the buffer, right, which I am basically wanting the consumer to write into, producer to write into. I pass that buffer as an argument in the procedure call. Okay. So let us take our old examples back again. The first example was doing physics and physics and maths averages together concurrently. Okay. So we saw the polling model for it. We started maths. We started the maths average. We started the physics average. We waited for both of them to be ready, and then we picked up the result. That's what we did. That was the polling model. What do we do in the producer consumer model? In the producer consumer model, we need buffers, right? And where are the buffers? The buffers are in the environment. So we don't want to leave this buffer hanging around somewhere. So it is nice to think about the producer as a consumer, as an object, right? The guy who is going to consume the result of this average. We like to think about him also as an object. So let us create an object which is called environment, the environment, ENV, and let us say environment has two fields called mbuff and pbuff that is supposed to hold the results of the average computation of math teacher and physics teacher. So the concurrent execution of math teacher and physics teacher average then goes like this. Math teacher starts average. Now remember, average doesn't normally have a parameter, but because we have set in producer consumer model, I will pass the buffer to them as argument. So therefore I pass mbuff as an argument to this function start. Physics teacher, I start with an average and pbuff as the argument. So I am telling you basically, physics teacher, you compute the average and you finish computing the average, you put the result in pbuff. I am telling the math teacher, when you finish your computational average, you put your result in mbuff. So there are two different buffers. So there is no danger that physics teacher will write into the math location, math teacher will write into it. There are two different buffers. Okay. Once I have started it, I can do something else. So the caller can go do something else. And after he has finished doing something else, whenever he has finished doing something else, he can check whether mbuff and pbuff are available, right? Available is a function now that we have to write. Who writes available? Who is implementing available? Environment has to implement available. The environment will check whether mbuff is fully written into, pbuff is fully written into, and if both of them are fully written into, that is the AND condition checks that, then I get out of that wait, right? So I am waiting till, so very likely that if I spent a lot of time doing something else, by then both those guys are finished and put the result in mbuff. So this available will quickly return saying it's done, and I can wait will not take any time, right? So just come out. But it's also possible that this doing something else is going to take very little time. I finished it quickly and I come here and I find meanwhile that guy has not finished. Average is still computing. In which case it is very much like the polling case, right? So now I am waiting for that guy to finish. It's fine. There is no problem. But it's also possible that I have a lot of work to do, so I did all that work. I came, meanwhile those guys have finished. They put the result in tray and they went on and did something else, right? They can attend to other customers. They can do average for other customers. So once I have the complete, once I have both mbuff and pbuff available, I can just take the value of mbuff and put it in average maths, pbuff and put it in average physics. I'm done. Okay. I don't need to go and fetch the result now anymore from the object, because the object has already given me the result. It is put into the mbuff. So we see basically that the onus now is on environment. The onus is not so much on class average, right? Class average does not have to implement these ready and result procedures, because we are not checking for ready. There is no need for ready to implement it. There is no result procedure because it's just reading mbuff, right? So no result is required. So average is just the same as before, except that at the end of average, after computing average, instead of setting some flag to true so that ready can basically be called to find out whether or not it's finished, instead of doing that, basically what average is doing now is it is writing its result in a buffer. Now remember, this buffer is in the environment. So it is writing, average is writing the result in a remote buffer, in a buffer that is far away. Okay, it will write it there. So that work it has to do, that is the extra work it has. Rather than that, it's a much easier job for class average now. Okay. And what does available do? Available basically returns true only if the buffer, whose its argument, is basically fully written into by producer. Now remember, when we had this discussion, we were talking about what happens. This idli is being served with chutney, and before the chutney was put on the tray, I took the idli away and all that. These kind of issues. How do I know that what I have written has been written fully? Before I wrote the full data, somebody could start reading the data and you will get nonsense. So the available function basically makes sure that buffer has been fully written to by the producer, and only after that it says it's available, right? So this basically ensures that the read and write operations of the buffer are atomic. Remember the word atomic, right? They are atomic. So therefore it basically makes sure that you can't do read and write at the same time. That is done by use of this available. Okay, so now if I want to do average and add student concurrently, it's the same, right? I have a buffer for average and I have another buffer field for we can ask, after all, add student never returns the result, right? Add student is not returning any result, so why do I need any buffer? Average was returning a result, so I need a buffer. But average never. The problem is that now we don't have a ready function, right? So we don't have a way of checking whether the fellow is finished or not. So we need to implement a buffer for add student, but it can just be a boolean flag. And when add student finishes its work, what it does is basically sets the remote boolean flag. That's all it does. Okay. So add buff is just a boolean flag. There's no result, but it needs this flag simply to know that it's finished. So the concurrent execution says basically start average, passing it average buffer, and for add student you have to pass it its parameter, which is new mark, and also pass this add buffer. Then you can do whatever you want, and after you have finished, you check whether both average buffer and add buffer are available. If both have been written into, then you read the average mark into average buffer. But the problem is of atomicity of that list. What we saw, that both the add student and average work on the same list. So one can be reading, another can be writing into the list, and we need to take care of that. That problem still remains. So we have to ensure basically that the atomicity or addition of the list is still respected. Other than that, we have saved the bother of writing ready functions and so on. So in some sense, this producer consumer model is a little bit more neater and nicer and easier to understand than the polling model. Okay, but one can use either. One can use this or that. So in summary, concurrency basically allows us to do several things simultaneously. We keep control of it by, in some sense, encapsulating the concurrency within objects, and and then in the objects implement basically procedures to unbundle the procedure call. They basically implement the start procedure, which starts the procedure, a ready procedure, which tells you whether or not the thing is finished, procedure is finished, and a result procedure to return the result. That is the polling mode. In the producer consumer mode, on the other hand, the consumer will create a buffer in the consumer object, will create a buffer and pass this buffer to the producer. The producer, when it finishes, writes the value into this buffer. The consumer can check whether the buffer is available, and if the buffer is available, then it can proceed. So in both cases, we are calling condition, wait for a condition to check, to wait for something at some point in time, right? In both cases, there is wait C that is going on. In polling model, we use ready to check, whereas in the producer consumer, we use available to check. Okay, so it's kind of similar, right? Kind of similar. So, and in both cases, basically, we had this issue of atomicity. We have to make sure that the list operations, two things can't be going on at the same time. One guy is writing the list, another is reading the list. This doesn't happen. So I hope you enjoyed these lectures on concurrency. We'll see you all next week, where we're going to look at yet another different type of programming paradigm, which is bottom-up computing, which we call bottom-up computing.